So first of all, thank you to the organizers and to the awesome talk beforehand, which is actually very deeply connected to the problem that I'm going to talk about today. So I'm filling in for my advisor, Chris Ray. Now, this has never happened before. I've never been asked to do work for my advisor. So it's a new experience, but hopefully I can navigate it. Anyway, so I'm going to be talking about Snorkel, which is a system, and data programming, which is a method that powers that, for generating what we call the new oil, so generating labeled training data and trying to make this process a bit quicker. And so I'm going to basically, well, first I'll start with the key idea. So this is not as new and shocking, even though it's in red font, as it was intended to be because of the talk preceding me. But from our practical experience in a different domain of applications, we are very convinced that labeled training data is the bottleneck in actually deploying machine learning systems today. And basically what this is going to be about, or the first 2/3 of this talk, is about how we can try and use lower quality supervision to train high quality models a bit more quickly than just hand labeling. So the outline, I'm going to start with sort of the applications that I work on and that a lot of us in the lab work on. And so the new branding from the top is dark data extraction, but you might have also heard information extraction or knowledge-based construction, and how this leads into the problem of getting labeled training data from our experience and practice. And then I'm going to talk about our approach for trying to do this a little bit faster. And then if I have time, and because it was on the schedule and I don't want to disappoint, I'll pitch a little bit of my lab mates' work on the systems and theory side of actually scaling up these algorithms. Cool. So I'll start with this problem of dark data extraction. And very broadly, we think of the world in terms of there being structured data, which is, imagine like an Excel spreadsheet or just a database table or a graph. It's all sort of the same thing, with a predefined schema that we're aware of. And this is data that's very easy to just plug into an analysis pipeline, whether it's more modeling that's being done or visualization or just end consumption. And then we have this great mass of increasingly accessible but not really usable dark data. So this is like unstructured text, images, video. It's sort of an expansive. I'm mostly going to focus on text here, which is what I do a lot of work in. So then this task of dark data extraction is, again, very, very simply defined as we're taking this sort of unstructured data and we're trying to extract it in structured form according to some usually simple schema that we've defined. And from our perspective, this is a very critical and often the most difficult step in a variety of analytics pipelines. So I'll go through a couple examples from current active collaborations now. Just to sort of give some motivation. So one thing that we do a lot of work with is with our collaborators is with extraction from clinical records. So clinical records have obviously electronic health records or reports of surgical procedures. Often, almost always have some structured data, and then they have some unstructured, like notes or the entire description of the actual procedure. And a lot of the valuable information is actually buried in that unstructured part often. So we're working with the interventional radiology department at Stanford now to basically help them pull out structured information from their procedural reports. So the chief there basically said that he has, he uses sort of 20 years of what he calls practitioner's experience to figure out, my understanding is very limited, but they're putting tubes into people tubes, catheters, to treat deep vein thrombosis events. And he has some intuition about what are the right matches between types of catheters and patient profiles. But he also has 20 years of reports he wants to be able to mine for more precise calibration. But it's buried in what he calls this verbal vomit of these long procedural reports that often describe multiple different catheters being inserted in multiple different locations. We're working with the I guess my slides are a little bit cut off, but it should be fine. We're working with with another group of collaborators and some medical records at the VA to pull out information on signs of post-implant surgical issues. So, basically manifestations of pain people have after an implant surgery. And again, the one underlying theme here is that a lot of the critical data is not coded up as structured data. So for like the hip implants, these are shockingly expensive. I forget the number, but I remember being shocked about it. And for whatever that's worth, that is coded up in the structured data fields. But often, pain and the specific area that it manifested after in follow-up visits is just documented as sort of shorthand notes. And we need both of these pieces of information to actually do analyses that we want to. We do a lot of extraction from the scientific literature. So we're working with some other collaborators and with the FDA to, again, pull out a very simple schema, just mentions in scientific articles of a certain drug potentially interacting with a certain type of bacteria in the gut. But we want to be able to do this at scale and with high precision recall. We're also doing some stuff on mining GWAS studies to make this more available. And we do some work with sort of defense, law enforcement, and political science type angles. So one new project that we just started up with some people who have very scary titles, but are former titles when they're in the military, but are extremely nice, is political science research on 20 years worth of sort of handwritten post-action combat reports and linking them to what are called exit interview reports, which I think is a euphemism, but I'm not sure. Either way, this is information on trying to do studies on what causes people to join insurgencies, especially when they're complex multi-party ones like in the Philippines, and what causes them to leave them. And again, we're just trying to get simple attributes out of the data so we can do downstream analyses on the structured data. And then there's a long-running project that was started before I even joined the lab that is now using some of the systems I'm going to describe, which is with DARPA's MEMEX project, and a bunch of district attorneys' offices use it to basically extract structured information from online sex ads to try and target law enforcement towards individuals that are being trafficked, and to try and model this. And then we're also doing some stuff in the lab. This is also not my work, but some collaborators where we're trying to move into images as well. So just as an example, to show a bit here, there was a recent Nature Communications paper that some people in the lab collaborated on, which was taking histopathology images of lung cancer tumors and actually outperforming trained histopathologists at assessing the tumor grade and bucketing patients according to survivability due to extremely high inter-expert disagreement rates. So there's a lot that's exciting here, and a lot of our motivation for the stuff in this talk is really about the fact that actually building these types of dark data extraction systems, still, like with our previous systems and others out there, takes months or years to do. And really, through interacting with collaborators, we found that this is not, it's often only useful if you can actually accomplish or train these sorts of models and get them running in hours or days, or that's at least our goal. But something shorter than months or years. And something that can evolve in response to the actual analytics pipelines that are being powered by this data. So this leads to the question, what is holding us back? If you guess it's about labeled training data, you were listening. Either way, even though you're probably all ahead of me by now, I'm going to start with just a little bit of grounding to lead into that, and also just to give a little bit more intuition for the actual problems that we're working on with currently with the system. So here's an example where this is an abstract from PubMed, and I'm interested in extracting a very simple schema, just 2 columns. I want to suppose I can tag. We use some existing toolkit to tag all the mentions of chemicals and all the mentions of diseases, and then I just want to train a machine learning model basically to consider every pair of a chemical and disease, and only pull out the ones that are actually mentioned in some sort of causal relationship. And so I just want to populate a very simple, 2 attribute schema. And this is a profile of the task, and it's difficult not because the schema is really complex, but just because of the high degree of variance in natural language. Probably very similar to naturally performed music. So what does this look like in a typical machine learning pipeline? This may look very similar to other machine learning pipelines, or should, that are not about relation extraction. Well, in our setting, we first define what we call some candidates. So this is some set of objects that we just decide what we have to train a model to decide whether they're true mentions or not. And then we annotate some of them. So we have experts sit down and provide labeled training data where they mark up some of these as the correct things that we want to train our model to extract. We traditionally would have to do some feature engineering, defining what are the actual attributes in this unstructured data that the model should look at. Such as, should it look at the verb in between the chemical and the disease? Should it look at the words in a window around? Should it look at some of the grammatical structure, etc.? And then finally, we train a model to predict which things should be extracted into our data set. So what are the things that actually take time and practice to do? So candidate extraction, we usually rely on lots of tools that are available, or on basic sort of dictionary matching. Usually gets us a decent start. And we rely on a plethora of open source toolkits like TensorFlow or scikit-learn, or really anything out there can do for this sort of simple binary classification problem. Traditionally, feature extraction was where we saw as the primary bottleneck. So it used to be that we would spend a lot of time, or people using the system would spend the vast majority of their time picking a good small set of features to actually comprise the model. So then comes the singularity, which we all know is here. And in particular, this is broader than just deep learning, but in particular, deep learning models for text, often like RNNs or LSTMs in particular, they can, to a large degree, obviate this challenge of engineering features by hand. So now we might react, okay, feature engineering is dead, right? This is actually why, from our perspective, people are excited about deep learning methods. The problem, however, is that this works if you have a massive labeled training set. So again, you already know the punchline, but that is sort of how we arrived at it in our practical experience. And so this is the problem. We have all these emaciated AIs, lying around begging for training data. My advisor wanted me to not make this talk too buttoned up, so there's that for you. Okay, so this leads us into, from our applications perspective, to the same conclusion that labeled data is very hard to come by, and this is really the driver of a lot of this progress we've seen in machine learning today. I should pause quickly. Does anyone have any questions? Most of this is just motivation to start. Okay. So again, a lot of this is due to this increased usage of deep learning, or just in general, people are using much more complex models, and this means more training data is needed, roughly. And if we look, as was pointed out, at a lot of the progress of these models, a lot of it is predicated on sets like ImageNet or other training data sets that are basically constructed over often years. ImageNet was done 2 floors down from us, and it took several years. And this doesn't even require domain expertise. It could be shipped out to mechanical Turkers who could label it as a car or a truck or a plane. So this problem only gets worse when we have a special domain like a medical or a biological domain, and when we have some task-specific training data labels that we need. And so again, just to emphasize, this is incredibly expensive and slow when you actually come head to head with it in practice. Especially on some of the problems that we see. It turns out that the grad students in like the bio labs that I collaborate don't take too kindly when I just say, well, can you just please label 1 million examples, and then we're ready to get started. And a lot of the big label training sets we see, especially where domain expertise is required, are painstakingly constructed over months or years by large industry or academic consortia. And another point that's not often made is that these are very static. So if you're looking at problems like we do, where the model we're trying to train, this extraction problem, is just the starting point of a longer analysis pipeline. This analysis pipeline in real-world settings actually evolves, and so, but the labels you collect doesn't, and it's not easy to sort of repurpose usually. So again, from our perspective, this is the limiting reagent in actually getting machine learning systems to work in practice today. So the question that we started asking is, can can we get around this a bit? Can we use noisier or sort of weaker supervision and still be able to train these high performance models? And so I'm now going to talk about one particular way, one particular framework and approach for doing that, motivated by our experience in information extraction, that we call data programming. So before I move on, any questions? Yes?
In healthcare, I think the problem is that you have a small sample. You don't have big data for train set. So how you struggle with this one? Because in healthcare you cannot train on a huge sample of data. Is that right? For example, if you for drug discovery or which treatment is the best for some type of patients, we cannot get a big sample. How you, because deep learning, you said that is for the big data.
So that's what I'm going to talk about here, and I'll I guess give one spoiler, which is that we are, as you can see from our motivational setting, we are often working in domains where we have access to a lot of unlabeled data. So that is one thing that we can try and leverage, and you'll see that in the method that I'll talk about. Yes?
Quick question. How does this all fit in the paradigm of semi-supervised learning?
There is a perspective, so let's go back to that question after I go through the method. It can be looked at from a semi-supervised perspective, and that we do get gains from using unlabeled data, but in a particular type of way. So we can come back to that after this part. Cool. So I'll go on now. These are my collaborators. That's the guy. The guy on the right is playing hooky, and the guy on the left is on the job market. If any of you are handing out academic jobs, you can just give it to me afterwards. I'll give it to him when I go back. Okay. So the key idea again is that is central to this work, is that we have a noisier or less reliable way of generating training data, but we know a little bit of something about the structure. And actually by modeling that, we can get away with using lower quality signals to train high quality models. So I'll unpack this. I'll start though with just a high level view of what the inputs and outputs in our system look like. So the input, and so data programming is the method, and Snorkel is the name of the system. The octopus logo is cut off in the corner, but the main point is my advisor wanted me to sound nasal in front of crowds when I have to talk about this, so hence the name Snorkel. So what happens is the user has some unlabeled data, writes a set of labeling functions, I'll unpack this, which are just scripts that provide labels to some subset of the data, and then just chooses some discriminative model to train. And then what goes on behind the scenes is that Snorkel generates sort of a noisy training set by applying the labeling functions to the unlabeled data, learns a model of this labeling process, so actually learns the accuracies of these labeling functions, and then trains a slight tweak of the discriminative model that was put into the system. And I'll focus first on what the primary user input is, which is actually just writing these things that we call labeling functions. So here's an example of what a labeling function looks like in the example I showed you about chemical disease extraction. So this is just expressing a strategy somewhat similar to the one that we saw in music, although a lot less inventive and sophisticated. But it is often called distant supervision and has been used sort of in an ad hoc way before. And this basically says, okay, if I see chemical A, bless you, and disease B in the same sentence, and I also know from some existing knowledge base I have that these are known to interact, then I'll just label this as true. And this is actually, very likely to be true. In this case it is. But it's also still noisy and inaccurate, because we could also have a sentence like this, and our labeling function will label this as a true example, and it's and just to give a little bit of grounding, we solicit these labeling functions, or users write them just in a Jupyter Notebook interface. So this is really the main interaction with the system from a practical standpoint, is writing these labeling functions. And one thing that we like about this is that this can be seen as providing a unifying framework for a lot of different types of sort of what was often called weak supervision, sort of noisy strategies for providing labels for data. And again, a lot motivated by ones that we've seen in people using in practice to get around this problem of label training data. So examples include distance supervision, which is very commonly used in the NLP space. Crowdsourcing, so getting lots of overlapping labels from maybe lay annotators who don't know the subject matter as well. Possibly using weak or biased classifiers to sort of bootstrap the problem, or applying domain heuristics or rules to generate these labels. And so we just sort of represent these all as these labeling functions, and they're pretty easy to express as just Python functions in the current framework. And users can also define dependencies between the labeling functions. So for example, if you have the functional form, so if you know that two of the labeling functions draw on the same distance supervision source or express a very similar pattern, you can express that there's a dependency to the system. And so implicitly, this collectively defines a generative model of this labeling process. So let me now unpack that a bit further. I'll start with what the actual pipeline of data programming looks like. So first, again, user inputs a set of labeling functions. We take these labeling functions as describing a generative model, and we learn this generative model. We essentially learn the parameters are the accuracies of these labeling functions, and we learn it basically by looking at where they overlap. And I'll unpack that in a second. And then we use this to train what we call a noise-aware version of the end model that we're trying to train. And then the output is a trained model that we can use to do something like chemical disease mention extraction. So now I'll go through these steps in a little bit more.
Noise-aware?
Sorry?
What's the noise-aware distributed model?
Oh, I'll go into that in a second. It's just a slight tweak to the loss function. Or not to the loss function, to the objective that we're minimizing. So I'll get to that in just a second. So the first step, I'm just going to try and give a little bit of intuition. So we're just learning a very simple generative model where we are, so here's a little diagram. These X's are the objects, so these would be a possible thing we want to pull out into our knowledge base from one of the from some unstructured text. And the lambdas would be represent the labeling functions. And so suppose that they overlap, and green maybe means yes and red means no. And so they agree and they disagree with each other. We look again intuitively at where they overlap, and you can sort of think of a majority vote type intuition of basically learning that if one labeling function is usually in agreement with all of its sort of co-labelers, then it should be trusted more than one that's usually like the lone dissenter when it overlaps with others. And this is similar to work that's been done in other fields with very similar models in theory. Different crowdsourcing is one example. Different if you guys are aware of this stuff, it's different constants but very similar different constants but very similar concepts. And from this, basically, we get the predictions of this model, which we think of as our sort of probabilistic or noisy training labels. And then the second step, this is the noise-aware model part. All we're doing is, in the standard setting, say you have a training set T, which is your data points, and you have labels that say this is, I'm considering binary classification. Say this is, exactly correct or exactly incorrect. And then we are trying to minimize just the number of times the model disagrees with these labels. Now we're just taking the expected disagreement because we have probabilistic training labels. So it's just a very simple tweak.
You're learning to predict the fraction that are labeled? Is that what you're doing?
So yeah, so some subset of the unlabeled, so we have a big set of unlabeled data points. Our labeling functions cover some subset of that.
Yep.
And then we're learning to, so say for logistic loss, we're trying to minimize the cross entropy. Sure. So another bit sort of just to give higher level intuition. these sorts of, sorry.
So, you're training on the labels that you got synthetically, but if your architecture is rich enough, you could just memorize these label functions, and then you sort of do perfectly well. I mean, by that I mean as good as you could with the communication issues.
Yeah, so,
So somehow you need to handicap your learning.
yeah, so I guess, so one of the assumptions we make is that the, which I guess most gets to this issue, is that the end labels are conditionally independent from the labeling function labels given the features. But I guess another bit of sort of intuition at a high level is that the labeling functions overlap. So we sort of have like a kind of information bottleneck where we can't exactly recover the exact labels of the labeling functions because all we're getting is their sort of combined labels on the points that they do label.
Right, but the point is, the optimal thing to do is understand you have like these 3 labeling functions and just go through that process and spit the answer out. So the claim is, if you really believe in the supervised learning pipeline, that's what should happen, right? If you have a vision of supervised learning.
Yeah, and we could take this further offline as well. I think, I guess another sort of intuitive answer is that, with 3 labeling functions, we probably could just memorize the labeling functions. And so, our guarantees require a certain sufficient number of labeling functions that have high enough overlap. But yeah, we can talk more afterwards also. Cool, so, yeah, and just to give maybe a little bit of a higher level intuition as well, there are previous methods where you just apply some of these sort of noisy ways of labeling training data and then treat them like they're ground truth. And you might have multiple different ones that are overlapping. And essentially what we're trying to say here is that, if one data point gets labeled, 10 times by 10 labeling functions that all independently agree, and another one gets labeled only once by one that sort of has low accuracy, the model should pay attention when it's actually training to those examples differently. So that's sort of captured with this simple semantics. So I'll just move on. And a bit of the sort of high-level theory results is that if you have a constant number of labeling functions with sufficient quality, average quality and average and sort of average overlap, and some other technical conditions, you can recover the same asymptotic scaling with respect to generalization error as with supervised methods. So you put in more on labeled data and you actually get improvement in your performance. This is the semi-supervised aspect. At this, given enough conditions at the same asymptotic rate as you would if you kept actually feeding in more hand-labeled data. But the even higher level takeaway point is that you get scaling with putting in more unsupervised data after writing your set of labeling functions. And I'll maybe breeze through this, but basically we tested on a lot of some of these information extraction benchmarks, and we see improvements over our previous sort of heuristically supervised methods, especially with deep learning models. And we've tried it out. I talked about a bunch of the collaborators, but some early experiences. We tried it on tagging chemicals and diseases, and in the span of a few weeks working with collaborators, we had sort of reached state of the art without actually using labeled training data. Cool. So that concludes the main part of questions.
So I'm trying to understand what you're doing. So you're applying the rules to sentences, right? And then whatever comes out is the label for the whole document. That's your supervised document.
In the dark data extraction setting, we're just. Sorry?
Can you repeat the question?
Oh, sorry. Repeat the question. So the question was that we're applying labeling functions to sentences.
I'm trying to understand what you're doing.
Sure.
Is that what you're doing? Like you're applying it to sentences, and then whatever comes out of those rules are what you're tagging the whole document, and that's your supervised learning.
Sure. So this is just to be clear about the divisions. This is, I guess, more a question about the dark data extraction task and how it's set up than the data programming method I was talking about. So just to clarify, so the actual object we're trying to classify is not the sentence or the document. It's, in this case, it's just whether or not this pair of of this chemical and this disease is asserted by the text to be in a causal relationship of the type we want to extract. So it's using features from the document, from the sentence potentially, but it's just about this particular pair the right one to extract.
So you're putting like essentially all of the documents you have, all the sentences, and you're passing all the rules, and you're giving some assertions.
Yeah. So, and again, there could be multiple of these per sentence, right? If there are, if you have a bunch of diseases and chemicals mentioned in the same sentence, then you have, all the pairs potentially to consider as things to pull out.
So you have the label appears for the labeling function, right? So the labeling function appears is all the whole label set, or is it? So what you have two labeling functions? One is very accurate on half the set, another one very accurate on the other half of the set. So each of them has a 50% accuracy, right? But combined, they will have 100%, but you don't really know that they have combined 100%. Something you would.
Yeah, this is a great question. So the question, I'll try and repeat it. Sorry, I was having a little trouble hearing. The question was, what if you have, for example, a labeling function that is very accurate on one part of the set and very inaccurate on another part of the set. Maybe you have another one that's, has the sort of flipped version of that. And so in the model that I'm describing right now, we have a very simple model. We're assuming that every labeling function we represent it by a single accuracy, and so it would not be captured by that model. There's some follow-on work that some people in the lab are doing with the ridiculous title of Socratic learning, so you can look that up, which is actually trying to correct this by adding features. So learning that there's a certain feature that divides the space, and if you condition on this feature, you learn a much better model of how accurate your labeling function is. You learn that it's actually really good on cats, but really bad on dogs or something. So yeah, that's a great question. Yeah. Yes?
It seems to me that the more complex the labeling functions become, the harder the actual data you're looking at is to label in general. The worse this will do. Have you found any particular data sets that this really doesn't do well on?
So most of our validation right now has been on these sort of text extraction problems, and I would actually break it down a bit more in that we sort of think of having different levels of supervision resources. So you might think of a high resource situation as one in which you have a bunch of labeled training data, in which case you either would need this solution, or maybe you would use this and you have some reason you want to add in some other heuristics to maybe solve a slightly different objective. We have a low resource scenario where you have sort of nothing to help you. So the really only types of labeling functions you can write are pattern-based ones. And then the one where we have the most success is sort of in the middle, where you have similar to Sham's example, where you have something to go on. You can do these hacks, or you can pull on these resources that are proximate to your data set, but they're not exactly the right supervision you need. That was an example is distance supervision. And again, a lot of our examples, especially in the medical space, they have lots of these rich ontologies, or say we want to just extract disease mentions. They have lots of different ontologies that sort of tag, that have disease names, but we don't have the exact mapping to this span of characters in the text is what you want to pull out. So it works very well in those sorts of scenarios, if that makes sense.
Have you considered using fuzzy logic as an aggregator?
That actually has come up before. I haven't considered too much, but yeah, I'm not as familiar, but yeah, I'd love to talk afterwards. Yes?
Sort of related to the question before that one, and also since we were talking about music before, I'm curious how you might apply this to an audio data set. I would imagine that maybe you could use digital signal processing heuristics and use those as your labeling functions, but maybe that's not random enough. I'm not sure if you thought about this at all.
Yeah, so I haven't thought a ton about it. I mean,
I think in a sense, this is why text is natural. You want something that'll get you off the ground. And the difficulty we had in the audio domain, we just couldn't even get off the ground by hard coding. So,
Yeah, so, and I think one thing is, if you had, so, what you did, if you had, if there were multiple sort of, different data sets that you could align through different techniques, then you could potentially put it under this framework. I don't know. I mean, I guess to some degree, it does depend on your ability to write these sorts of labeling functions, which is very domain and task specific, or especially sort of, data type specific.
Where you are now, and how sparse can your labels be compared to where you hope to get to? So you have some labeling to get where you're going.
Yeah. So the question is, how sparse can the labels be over the data set? I guess to some degree, we don't know. So one thing is that in practice, people tend to write very precise but low recall labeling functions. So the performance is not that bad, even if they don't overlap a ton. But we can't learn as much about the labeling functions if they don't overlap enough. So that's the boundary we run into.
What is it about the feature extraction, which is automated through that's compared to the learning functions that makes it so one is something that humans have to hand, just coding the other one isn't?
I guess so. That's I guess that's so. The question was, what is it about about deep learning that allows you to? Or,
why do feature extraction? Why do you get that for free, but you don't get the learning functions for free?
Oh, why do you not get the labeling functions for free?
Labeling functions, yeah.
Well, your supervision has to come from somewhere, and the reason you get the features for free to some degree is because you're effectively considering a much more complex space of models. So that the trade-off is you consider you sort of throw the whole kitchen sink in there. You consider a very large complex space of possible models to learn, but then you have to provide more supervision. So there's no free lunch in that sense. Maybe that.
Yes. So in your example of the chemical and disease pairs, in your deep learning model, is the feature then the pair, the chemical and disease pair, or are you using the labeled data to then train a deep learning model which will take a text and spit out? Yeah,
the latter. So the question was, what are the actual features in the chemical disease extraction? So we would use we're labeling this object, which is this pair. The labeling function can pull upon the surrounding context, and then the model we're training is also going to pull around the surrounding context, and probably in general much more sophisticated set of we use different linguistic features as well in those models that are much more fine-grained. Yes?
You said the quality of the result improves as you add more unlabeled data. Can you maybe explain how that works, or get the intuition behind that? Why does adding more unlabeled data help in this process?
So I guess I could give a little bit of intuition maybe with this example here, which is that suppose in your unlabeled data set, you're going to label anything that has chemical A and disease B as true because you saw it you have it in your small distance supervision knowledge base that you already have. And there might be many synonymous ways of expressing this relation in text that occur in your unlabeled data set. And they'll all get labeled by your labeling function. So this already gives you more information. Without actually, you're only still writing this one labeling function. Similarly with, if you write a labeling function that's a regex, say, some pattern, there will be variation in the different examples that it will tag. And that variation might actually, contribute to features that your more sophisticated model learns.
So it's the more sophisticated model that is able to do better as you add more unlabeled.
Yeah, it's the end extraction model you're training that does better. Yeah, and also so this is. So the end model on the right does better for that sort of intuitive, that's the intuition about why it does better. And the generative model also does better as well because you have more instances of overlap between the labeling functions to learn from.
Or to be our at time.
Or at time, okay.
So, feel free to hang over the various questions. Who's going to wrap Alex? Or